Hello there. In this video, I'll be talking about how to make a very efficient array in Game Builder Garage. So if you're unfamiliar with the topic, an array is a very common structure in programming languages, which basically is a place where you store a bunch of numbers that are very easy to access later on. So for example, here I have a demo for an array with 16 items in it. So for each slot, I can set a specific number here, and like each one of them are independent of each other. It can be anything I want. And then for each spot in the array, it has a index. So in this case, the index goes from 0 all the way to 15. And how arrays work is basically how arrays make things easier for programmers is you're basically able to store all these numbers in one spot, and you can access them easily if you just remember the index of that specific number. So for example, I want to access a number at index 1 here. So when I set index 1 here, I can access it and like add stuff and subtract stuff of it, and also read the value from the specific number. So in this case, it's outputting 7. And if I change the index here, so for example, to the index 3, is going to be pointed at this number. And yeah, I can see the value 2 here, and I can edit this number independently of everything else. So basically, it's a easy way to organize your code and store lots of information that are easy to extract. Now, in this video, I'll be showing you how to make this extremely efficient array architecture here. But this specific array structure here makes use of a mechanic in Game Builder Garage called subframes. So subframes is a very deep topic that not a lot of people know about or really understand. So I won't actually go too deep into how the subframes and how everything in these nodons actually work and how everything goes together and does things. I'll just be showing you how to make your own arrays, how to send inputs to it, how to control it, and how to get outputs from it, but not necessarily how exactly it works. That will be a topic for a different video. Now, before we begin with this structure, let's first start with how would we implement an array in the first place without using this. So what if we just used normal GBG mechanics that we're already familiar with? So here I made exactly that. So here's an identical demo, which yeah, it's basically the same as what I showed earlier. And instead, it's made purely using traditional GBG logic that you're probably familiar with. So let me just run you through how this array would work, or how you normally code an array. So yeah, the first step is, well, let's say we want to write into a specific counter. So for example, we want to be able to send numbers into just one counter and not any of the rest. So the easiest way to do that is by using something like this. So here I have the index stored in this counter here, and it's going to just map into this bullseye, and if I press these buttons, I can control which bullseye is activated. Now, each of these bullseyes activate a specific multiply nodon, and then the input is then sent to the second input of all these multiply nodons, and all these multiply nodons go into the counters. So for example, when the bullseye is set to like the second position, when I send an input here, it will only be able to get sent to that specific counter because only that multiply is activated. And if I go to the other ones, you can see there, yeah, only that is being accessed. So only one at a time is being accessed here. So that's how you make a structure for writing into a array. The next question is, how do we extract a specific value from a specific counter? So right now, we have all these counters. If we just add all of them together, for example, here you have the value of 2 there and value of 3 there. Well, we can't just add them all together because all of these numbers are going to add together. So what we need to do is to add these next second row of multiplies here, and we can reuse these bullseyes here to activate these multiplies. And yeah, when each of these counters here are connected to their own multiply node on at the bottom, well, because of the bullseyes, when for let's say we send the value of 3, 4 in the first counter there, and like 5 in the second counter there. Well, since the output of the counters are being uh, gated by the multiply nodes there, only the specific index that's selected will have its output sent to this output wormhole and get sent to this number node on here at the bottom, which is our output. So for example, here we're selecting the fifth counter here where there's no zero value. But when we go to the fourth bullseye there, we're activating that fourth counter there, which has a value of 2, and you can see the output value of 2. And if we move to the left one more time, it's 1, 5, and then 4. So that's basically how you would typically make an array in Game Builder Garage. Now, as you can already see here, making an array in Game Builder Garage normally is very costly. Like, imagine for each number that you want to store here, you basically need one bullseye, one multiply for the input, one counter for storage, and another calculator for the output. That basically amounts to 4 nodons per number that you want to store, which might not be worth it in like very nodon starved applications. So that's why typically you won't see many people using count arrays in Game Builder Garage because it's kind of inefficient. It's very costly to do that. But here, if we use the subframe method, you can see that we're storing the same amount of numbers here. So this stores 16 and this also stores 16. But you can see here that basically the only thing that's repeated for each number that's being stored is just one nodon. So instead of costing 4 nodons per item that we're storing in the array, now we're basically just costs 1 nodon for storage, which is a very incredible nodon save on the traditional solution. So let's try to build one on our own. So the first thing we need to do is to build a 3-map structure that I like to call the Subframe Clock. So it's basically the heart of most subframe coding. And sometimes it's also called the Omekari oscillator, since it was originally invented by a Japanese programmer called Omekari. I won't go too much into how it actually works. I'll just show you how it's made. So first, make a map and have input setting of 0 to 1 and output setting of 1 to 2. So I say it, don't touch any of the other settings. Next, make the same map again. Just copy that and put it there. And then lastly, make a third map, and for this third map, set the input range to be 13 to 14, and then the output range to -16 to 0. There, 13 to 14, -16 to 0, inverted, and range restricted. And that's basically those settings, and then connect all of these maps in a crisscross pattern like this. There, that's basically set up. Double checking all the settings. And yeah, most subframe applications start with this, and maybe you'll learn why when we get to that video. The next step is to create our storage module. So the storage module for this type of array is just made up of a bunch of calculator nodes. Calculator nodes are typically useless for most people, but this application actually has some kind of uses. So I won't go too much into why they're actually useful here, but yeah, I just make them here. So in this case, for this example, let's just start with a system that stores 16 numbers. So actually, the number of items that you want to store is actually quite specific here. You can't just choose any number. 16 is one of the numbers that you can choose, and I'll show you later how to do it with other number of items that you want to store in your array. But for this example, just start with 16. So yeah, Let's take the number of calculators that we want. So here we have 16 calculators, and then let's connect all of them right uh, consecutively right next to each other, and finish a loop here. So basically all of the calculator nodes are just connected in just one big loop here. So you can imagine all of the collections going around in a loop. And next, we just take a equals comparator here, connect the middle of our subframe clock to one of the inputs comparator here, and then a multiply here. Either input works. And then now we have the basic a storage module. So for example here, let's say this counter is the index. So this is the number that chooses which of these we want to access. And let's say this is the input. So let's connect the input, one of the inputs of the multiplier here, and then the index to one of the inputs of the comparator. So the comparison is between the subframe clock and the index, and that goes to the multiply, which has this comparison and the input, whatever input we want. Now let's take this multiply node on and connect it to the third calculator here. And any input doesn't matter. It's connected to the third input here. Now we can try it out. So let me replace this with a button so that it is an input. So here, hit on press. When we press A, you can see that this specific connection lights up. Let me take a router here to show you. So this calculator here, which we'll call calculator 0, is being sent the input. So that whenever I press A here, you can see that this specific connection here increases. Basically, this input is going into this array and just going into this specific output here. And you can see when we connect the other arrays to other number objects, you can see that the number is not going through to them. And it does me again. So yeah, there. Only being sent to index 0. And if we change the index here, for example, index 1, when you press A again, it's going to get sent to this one. And then let's say index 3 is going to be sent to this one. And that goes from 0 all the way to 15 here. And then 0. So that's the basic way to send inputs to this array. So here, to make it a bit easier to follow, I just added a number object for each number in the array we're connecting to. Change the index number here so I can change it on the fly. And then added these extra buttons to the input so that I can increase and decrease whatever input or whatever value that we have in the array. And so with this same setup that we have earlier, just these three maps, these storage modules, this comparison, and this multiply, we're already able to make a very simple array that we can just write into and just take the outputs individually from each of these additional nodes. Let's say you don't really care about using the index to choose which output to output. You just want to have 16 different outputs that you just access on your own. That's, yeah, with this system, with these few nodes, you can already do it. So like just a showcase here, if you like increase index 0 there, like move to another index there, subtract, then add, so on. There we go. We have 16 different numbers that we can take the output of individually. Now, what if, let's say, we don't want just that, we want something similar to the thing I showed in the demo, where using the index, we just have one output and we use the index to select which number in the array we want to be sent to that one output. For that, we just need to add a little few nodons here at the bottom here. So first we take a subtraction calculator, an inversion calculator, and a multiply calculator. That's all we need. So for here, we take the output of the negative calculator, go to the input of the inversion, take the output of the inversion and send it to the second input of the calculator that matters, not the first. Send it to the second input. And for the multiply, connect its output to the top input of the minus calculator and the input of the inversion. And lastly, we take the output of the inversion and send it to one of the inputs of the calculator. Then next, we take the output of the comparison that we had earlier and send it to the other input of the calculator. And lastly, we take the output of the first calculator in our array and send it to the same input where we sent the output of the inversion node on. So just to recap, for the inversion node on, it goes to the one of the inputs of the calculator, multiply calculator, and the negative input of the subtraction calculator. Subtraction calculator goes to the inversion node on. The multiply goes to the top input of the calculator and the inversion node on. And for the multiply calculator, one input is connected to the comparison, is connected to the clock and the index. And the second input has both the output of the inversion and the output of the first calculator in our array. And with just these three nodons, we already have what we want. So just to display that here, this number nodon set index 0. So when we increase the value at index 0, we can see that there our number is currently at 6 and it's displaying number 6. And if we change the index, let's say 1, now it becomes 0, and it just reads whatever the value is in index 1, and like change to like whatever random index that we want. You can see that, yeah, as we change the index, it displays the correct value for whatever is selected at a time. Actually, one more fun fact about this is that this thing actually has two outputs. So if we take the output of this inversion nodon instead of this calculator nodon, it is actually the inverse of whatever our output is. So in case you need the inverse of the value of the array for some reason, you don't need to add an extra inverter nodon. That shave is already built in this system. For example, yeah, like store number 7 or like 2, like 3, you can see, yeah, the output of the inversion is just the inverse of whatever value that we're actually storing there. Actually, one very useful use case for this inverted output would be if you wanted to set the specific value of one of these numbers in the array instead of just adding to them. Because like right now, we're just adding or subtracting certain numbers for here. So maybe in your case, you don't want to do that and you just want to set it to a specific number. In that case, the easiest way would be to send the number that you want to set it to and the inverse of the current number. For example, here the value is 4. And if you want to set it to the value 10, then you just send 10 minus whatever is currently inside the array. So that's basically 10 minus 4, which is 6, and this will become 10. In that case, instead of just having to do that extra calculation with some extra nodons, we can just feed this negative output back to the input that we want. So we just add this to the input. That's basically like 10 minus 4, and we instantly get 6. That's one way that we can use this inverter nodon. And that's basically it. A complete, very efficient array using just 3 maps, 1 comparison, 1 multiplier, another multiplier, subtraction, inverter, and 1 nodon for each number that we're storing. Well, what if you need to store less than 16 numbers? Well, as I mentioned earlier, The number of numbers that you can store with an array here is quite particular. So as a rule of thumb, the numbers that you can choose must be a factor of 16. Basically 16, 8, 4, 2, or 1. So what I mean by that is, say here we have 16, so that works. If we want to just store 8, we can just remove 8 of these, then reconnect this position all the way here. See here, it works the same as earlier. Now this is index 0 and this is index 7. See here. And then it's 7, it goes to that. Now, since we're using something less than 16, something interesting happens when we go beyond 16. So now if, say, go to index 8, what will happen now is it will actually go to index 0. So let's see here. Yeah, right now it's set to index 8, but I'm setting on the input it's going to index 0. Basically, if you use a index, or if your array has less than 16, the 16 indexes are still used. You'll just have certain numbers in your array reused for 2 values. So right now, with the array size of 8, the rightmost number here uses index 0 and 8. This is 1 and 9, 2 and 10, 3 and 11, and so on. So if you're going to do something like this, make sure that your index, you just limited your index from 0 to 7, so to prevent any confusion. And if you want to use 4, do the same thing. Just delete this 4, just have this array of 4. Click this back here. And now this is, index 0, index 1, index 2, index 3. Index 4 goes back here. Index 7, index 8 goes back here, and so on, all the way to 16. And yeah, make sure you just limit this to 0 to 3. Now, what if you want to set the number to something between those numbers? For example, I want to set it to 12 numbers in the array. In that case, we don't really have much choice here. We just have to select the number that's bigger than the number you want. For example, for 12, the next biggest number is 16, so we just have to use 16 and just don't use 4 of the indexes. Yeah, we can just use like 0 to 11 and then just ignore these last 4. We can't just remove like 4 of these and just reconnect this. Because of how subframes work, that is not gonna work. Let me just show you here. Like for example here, just send the value here and you can see that the numbers kind of just glitch out. And yeah, all the number, like I'm trying to send the 1, but actually all of the numbers are updated at the same time and they're blinking and they're glitching out. Yeah, that won't work. You need to set the array to values of either 16, 4, 8, 2, or 1. Now, what if you want to store more than 16? Let's say we want to store 32 numbers instead, so that's double of what we have right now. To do that, it's pretty easy. Let's just take all of this whole part, and just copy it. So we basically have 2 arrays. Then what we need to do here is, for this one, we remove the subtraction calculator and the inverse here at the output. Then for input, we send the same input to this multiply. We send the same connections to the comparison here. So the subframe clock here and the index here. Now the extra thing that we need to do here is to add a value of 16. The same input as the subframe clock. So that's this input, this top input. So yeah, we just added 16 there. And lastly, for this multiply at the bottom, we send its outputs the same as this one. So you just send it to the top input of the minus calculator here and the input of the inverter. And then we also take the output of the inverter and send it to the input where we sent the first calculator of the array. And now we're actually all set. So just to show you here, index 0. Yeah. Index 0 is sitting there. And then this goes all the way up to index 15. You can see index 15 is over there. Yeah, see there. And then when we move to index 16, now whenever I send an input, it gets sent to this calculator instead. Then I move up. It all works normally. This top array doesn't get affected, and this goes all the way up to 31. Yeah, there's 31. And you can see that the output is still shared between the two arrays. Again, you can imagine the same thing for even bigger numbers. Let me just this to go up to 48, and then I do the same thing here. If you want to make this 48, do the exact same thing, just change this to 32. So now this array is going to be 32 to 47. I just do the same things that I did before. So this goes here, index goes here, input goes here, this goes to these two nonons, and then the inverse goes here. Now when we go all the way to 47, you can see that one, the one at the very bottom left, is activated. And you imagine the same thing for indexes 32 all the way to index 46. And then same principle if you want to reduce the number. Like say we want just instead of 32, what if you just want 24? In that case, we can just treat this second array, just make the second array into just 8. So yeah, count, that's 8. So now we have two arrays, this 16, this is 8, and it's going to be a total of 24. So now, like if I do this, if I go to index 15, you can see it's there, index 16 becomes this bottom one, and then this leftmost one is index 23. And the same doubling up happens as before when we had the 8, 24. I guess we have to hear it. That's 25 again, 26, all the way to 31 there at the bottom left. Now, one last thing I need to warn you about is if you need to extract signals straight from this array. If you're reading from the index in the array and getting the outputs from here, that's perfectly fine. You can treat these two signals just like normal signals that you're already used to. However, if you need to get signals straight from a specific position in the array constantly, well, if it's direct, like if it's, for example, here the number node is directly connected to this array, that's fine. It will work exactly as you expect. And like, for example, if you take a counter connected directly to this calculator, that works exactly how you would expect. However, if you need to pass that signal through maybe like a multiply calculator or a few more calculations, basically, if you need to pass the signal through any of these 12 neurons, then you might have a problem. You can still do it, but you need to do a little bit more stuff that maybe might not make sense to you right now. I'll just tell you how to deal with it. So, yeah, if you need to pass that signal through any of these neurons, it will not work as you expect. So let's try it out. So for example, you want to, let's say, take the output of index 2 and then add like a constant 5. And then let's just take a project to display what is going on here. So right now it's 0, so this makes sense. Now if I move on to index 2 and increase this, you will notice that, well, even when this is connected to what's supposed to be 11, the output here is still 5 for some reason, so it's not updating. And if I move to index 1, you notice that actually it's not taking the value at index 2 anymore. It's actually taking the value at index 1. So you can see here, even though I will take from what's supposed to be index 2, the output that we're getting here is the output in index 1. So it's like index 1 plus 5, 14. Basically, if you need to use any of these nodons, for each nodon that you add, that you need to send the signal through, you need to offset where you get the signal from by 1 nodon. So what I mean by that is, let's say here, we want to add 5 to the signal that we get here, and we want to pass that through 1 nodon. So since we're passing it through 1 nodon, instead of taking it here directly, we move 1 nodon to the left and then grab that output instead. In this case, you'll see that if I move to index 2, now it works like we want. So it's getting the value at index 2 and then adding a constant 5. Like, for example, if it's like multiplication, whatever this nodon is, just as long as it's 1 nodon in the direct path, it does the same thing. So index 2, index 1, index 2. Yeah. It's multiplied by 5. And the same thing regardless of which of these 12 nodes you use. And for example, if you want to pass it through 2 nodons, for example, let's say you want to maybe invert it and then multiply it. So now this is, we need to pass it through 2 nodons. In that case, if you want to apply this calculation to this value, you need to move 2 spots here. So get this, grab this signal, put it here, and you'll see that when we go to index 2, it works exactly how you expect it to. So now 9 is inverted to -9, then multiplied by 5 to become -45. So basically, like an easy way to visualize this is to connect. Like if you're gonna connect nodons from this, you place them right like this in like right next to each other, like here. So like for example, like imagine we have 5 nodons in a row. Yeah, we need to put a signal 5 nodons in a row, and we want like the signal here specifically in this column. Well, we arrange the nodons like this so that the output that we want aligns exactly where the input that we want is. So like we want the input to this whole system to be whatever this value is. So we align these nodons that we're going to pass it through and put the output at the same place where we expect this to come out. And just connect the first nodon over here. Another thing that you can do, what if you need to do operations between 2 different numbers in the array? In that case, you do the same offset for both of those inputs. For example, let's say we want to multiply this value and this value. Well, if we want to get this value, we offset it by 1, so we connect it here. And if we want to get this value, like the value comes out here, so we offset it by 1, we get it from here. So you will see that if I set this to 1, set this to like 2, there we go. We're able to multiply these two array values. And you just have to look forward to the eventual subframe tutorial videos if you want to understand why it is like that. And that's it for this video. See you in the next one.